Good evening, everyone. So my name is Jyoti Sharma, and this is week 5, and this session will be from 7 to 9 only. So am I audible to you or not? Can you just confirm me? Can you write in the chat box whether okay, Venkateshwara, thank you for your response. So what we cover today? So because this is a week 5, and in this week 5, this is lecture 21st to 25, and here the content is, first we will see through different processes what kind of gases are released. The first thing. The second thing is, because the most problem that we have today in the environment is that we do have particulate matter in the environment, the first thing. And second thing is, we do have dangerous gases in the environment. So our focus is to remove this particulate matter and and that dangerous gas that we have in the atmosphere. So what mechanism we do have, what kind of instrument we have, what efficiency of each instrument we have, so that we will discuss. So for the particulate matter removal, we do have scrubbers, we have gravity settlers, we have ESP, that is the electrostatic precipitator, then we have baghouse and the cyclone separator. So this will be covered under the removal of particulate matter. Then we will cover how we can remove various gases. So this can be done by absorption, adsorption, and like we do have different kind of absorbing material to remove SO2, NO2, and CO2. So we will try to cover this all. So I'm starting with so again, this is a very simple. I have a lot of MCQs question, and you have to respond me. And please don't worry even if you are giving me wrong answer, because this is just the discussion between you and me, and we will try to solve, we will try to discuss about each of the terminologies that are important for us for this lecture. Okay, so I'm starting with different processes and how different processes is giving you dangerous gases or particulate matter in the environment. So one of the process is pyrolysis. So during pyrolysis of waste plastic, which of the following harmful pollutant are generated and needs to be removed? So we have four options: NOx and SOx, CO2 and H2O, HCl and dioxins, H2S and COS. So you have to give me answer in your chat box. Even I will encourage you, if you want to speak, then it is also nice for me. So I will wait your response, and if you will not give me, then obviously I will give you the right response. Okay, let me see the answer. Venkateshwara gave me A or D. Uh, Not exactly A and D. And one person, Vaishnavi gave me answer A. Uh, Actually, I just want to be very particular about the answer, because SOx and NOx are very general gases that are being released by vehicular emission, by combustion, by any industries whenever we do have the combustion. So these are very common gases that has been released by different type of processes. But I want to get very specific gases that are being released by pyrolysis. Okay. Someone changed the answer. Okay, Priscilla gave me C answer, and yes, I agree with this, that this is the right answer. So, the first thing is, you have to understand what do you mean by pyrolysis first. Okay, and how pyrolysis is different from combustion. So, can you tell me the difference between these two? One process is pyrolysis and another process is uh, combustion. So what's the difference between these two processes? Do you know the differences between these two processes? Okay, uh, just I do have little description about this. So pyrolysis is a thermochemical decomposition of organic material at high temperature in an inert atmosphere without oxygen. So it means whenever we are talking about the combustion, there is oxygen. So in the presence of oxygen, we are decomposing something, right? But if it is a pyrolysis, the first thing is you are doing the decomposition of organic material. The second thing is we are decomposing it in the absence of oxygen. So this is, and the third is at the very high temperature. So these three characteristics will define the pyrolysis. And this pyrolysis is very important for us because whenever we do have plastic material and some other sewage that we have, and if we want to decompose it, most of the time the one of the process that we use is pyrolysis, because it can give you char, if you have heard about this. So this char, this is the end product of this pyrolysis. If there is any plastic and that is undergoing the pyrolysis, that will give you char, and char we can use as a fuel. Okay, so that will give you the energy. So that's how this pyrolysis is very important whenever we want to decompose or degrade something. Okay. And but the thing is, there is HCl and dioxin. Dioxins are carcinogenic in nature. It means these gases can cause the cancer. So that's why paralysis is very harmful until or unless this paralysis is happening within a sealed box. Okay, or at the sealed place. So that's how this paralysis should be under very controlled condition. Otherwise HCl and dioxin may release into the atmosphere, and that can give you the cancer causing effect, right? So this was about the pyrolysis. So this is the one process by which dangerous gases can be released, but on the another side, plastic like material can be degraded. And third is it should be in a very controlled manner. This is, I think you can see here, even if we do have tire or plastic. So if we do have high temperature heating in the inert atmosphere, and then it can give you the end product charcoal, bio oil, or biogas. Okay, so the next question is, which process produce biogas containing mainly CH4, that is methane, CO2, and H2S? And we have four options here: gasification, anaerobic digestion, combustion, pyrolysis of biogas. You can give me whatever answer you are thinking is right, and otherwise I will tell you whatever appropriate answer that should be. So here we do have four terminologies: gasification, anaerobic digestion, combustion, and pyrolysis of biomass. And okay, Venkateshwara gave me a D answer. What I'm saying is, if it is a biogas, like methane, CO2, and H2S, not just the pyrolysis, but gasification and anaerobic digestion is giving such kind of gases. So these three may be right answer, but if we are talking about the percentage, then anaerobic digestion is giving you the highest percentage of biogas, that is CH4, CO2, and H2S. But your answer is not wrong, because pyrolysis and gasification will also give you biogas. Now the thing is, again we have to know the difference between gasification, anaerobic digestion, combustion, and pyrolysis. We already know about the pyrolysis, so there is no any problem with this. Okay, combustion. This is very general term that we use, and this is whenever we are decomposing something in the presence of oxygen. So this is combustion, right? We are burning something in the presence of oxygen, then that will known as the combustion. Anaerobic digestion. This anaerobic digestion is very much similar to the pyrolysis, that it is in the absence of oxygen. But the thing is, here we are using microbes. Here we are using microbes, the microbes that can live in such kind of that can live or survive in anaerobic condition, means in the absence of oxygen. So in the presence of microbe that can survive in the absence of oxygen will decompose your organic matter, so this will come under anaerobic digestion. And most of the time whenever we are producing that fertilizer or manure, so uh, uh, that is just the end product of anaerobic digestion. And if we are talking about the gasification, then this is under high temperature. So here the temperature is very high, but oxygen is given but not fully, it is partially. So this is how we do have different processes that can give you different type of gases. Okay, so I think I also have something. B is the right answer, that is anaerobic digestion, but I'm not saying that A or D is the wrong answer. This is also the answer, but mainly the percentage of biogases are being released by option B. So just see here the differences. Gasification, the temperature should be 700 to 1000. Anaerobic digestion, because here we are using microbes, and the temperature will be just 35 to 55. For the combustion, the temperature may be more than 1000, and for pyrolysis, the temperature will be 300 to 600. If we are talking about the oxygen gasification, we will have very limited oxygen. Anaerobic and pyrolysis, this is the absence of oxygen, and in combustion we need excess of oxygen. Then main product will be syngas, that is carbon monoxide, H2CH4, char and tar. Anaerobic digestion, biogas, that we already have in the question. For the combustion, because combustion is in the absence in the presence of oxygen, then we will have oxygen in each of these molecules. Then we have pyrolysis, that again will give you bio oil, syngas or biochar. So this is how we can differentiate between the processes. I think this is clear. Even if you the things are not clear, you can let me know, I will try to discuss it in more detail. So should we proceed further? Okay, thank you so much for your response. The next question is, which of the following equipment is specifically used for the removal of particulate from gases? And we have four options here: a wet scrubber and absorber, a gravity settler, ESP, cyclone, fabric filter, adsorbent and absorber, and catalytic converters. Venkateshwara gave me B. Can I get more answer from more people? Okay. So, yes, I agree with this answer. That is B. But why the B, not A, C, or D? So, if we want to remove particulate matter from the gas, so our purpose is to remove the particulate matter, and for this, if we are talking about the wet scrubber, then yes, we can use wet scrubber for the removal of particulate matter. But if we are talking about the absorber, then this is for the gas, so that's why A is not the right answer. We can use we will talk about this gravity settler, ESP, cyclone, fabric filter at length, because the whole session is all about these kind of instruments only. So these are the instrument by which we can remove the particulate matter. uh, Adsorber and absorber, these are the part of gas removal. So this is not for the particulate matter removal, this is for the gas removal, so this is not the right answer. Catalytic converter, these are used in vehicles when we want to change NO2, let's say NO2 in N2 or the inert gas. So this is how so this is again the removal of or the conversion of NOx or SOx into inert gases. And this kind of this converter we do use in the vehicle, in the engine. So this is again not the right answer. So the right answer will be gravity settler, ESP, cyclone, and fabric filters. I'm going to the next question. Okay, so I just wanted to show you the figure. So this is the figure of your settler, gravity settler. So under the gravity, so here the gas will come in. The particulate matter will be deposited here due to gravity, and gas will go out. So this is your gravity collector. Then coming to electrostatic precipitator. So from the name only you can say we do have some charge, electrostatic. So we have positive charge and negative charge. So what we can do is we may have some electrode that have the positive charge, and the gas that is coming in, that is the gas coming in, we can give them the negative charge. So what will happen if this gas or particulate matter will collide to this positive charge, then it will neutralize, and this is how we can collect the particulate matter. So this is something positive, negative, neutralization, and then the collection of particulate matter. uh, so this is the one another way. Then the next is cyclone. So we have cyclone in which what we can do is the gas will come in that have the particulate matter, and because that will collide to the outer boundary of this, and this is how all the particulate matter will be deposited down, and the gases will clean gas will get out. So this is the cyclone. Then this is your fabric filter. So we have fabric made filter because fabric is woven, each have some pores. So whenever the gas will cross with the particulate matter will be stick to your filter, fabric filter, and this is how we can remove particulate matter using fabric filter. And now we will talk about such kind of technologies, instrument, one by one. So I don't think that there is any problem. So we will start our things with gravity collector. Let me remove this. Okay, so the next question is, which process equipment can remove both particulate and gas molecules simultaneously? And we have four options here: wet scrubbers, gravity settler, fabric filter, dry adsorption. What do you think? What kind of material technique we have that can remove both? Priscilla gave me A and Venkateshwara gave me C, but I'm agreeing with A right now. So this is wet scrubber. So what will happen in the wet scrubber? uh, I will show you the figure, but gravity settler we already have talked about this gravity settler. So this is just for the particulate matter. If we are talking about the fabric filter, so until or unless we have some media, some chemical in it, so this will just remove the particulate. Otherwise it can act to remove particulate and gas molecule, but most of the time we have just fabric, woven fabric, but we are not using any chemicals in it. So the thing is, it can just remove the particulate but not the gas molecule. Dry adsorption is for the gas removal but for not the particulate matter. So the right answer will be wet scrubber. And let me tell you, so scrubber means we will have so the thing is, we do have some instrument and that have some spray. Okay, so let's say it is having some spray of some chemical. So this is the chemical spray. So that chemical can absorb the gas molecule, the first thing. Okay, and what will happen, that particulate matter, this spray can deposit your particulate matter at the bottom in the form of sludge. Okay, and then clean air will go out. So this is how, so scrubber means some chemical that can absorb or adsorb your gases. Okay, and wet means we are using some chemical that is liquid in nature, and this is how whenever we do have particulate matter as well, that can be deposited because we are having the spray of that chemical. Okay, so this is how the wet scrubber can remove both particulate and gas molecules simultaneously. Maybe I have figure of wet scrubber. Okay, this is what I was talking about. So here we do have gas. That gas may have particulate matter. That gas may have SOx or NOx, that is nitrogen oxides or sulfur oxide. And there is a spray. Okay, what will happen? That spray that spray may have limestone. So the purpose of limestone is it can neutralize SOx. Okay, so it because it is absorbing, there is some chemical reaction between limestone and SOx or NOx. Okay, so this is how we can remove the gas. And for the particulate matter, because spray is coming out from the top, so there will be deposition of your particulate matter and the clean gas will go out. So this is how it can remove both. Okay, so now we will talk about these techniques, this instrument one by one. And our first instrument is gravity settler. This is very simple, and we do have a very simple question on it, but we will try to have a good discussion over gravity settler. Okay, so what is the main purpose of a gravity settler? We have four options here: to remove very fine particle, to settle large abrasive particle, to adsorb gaseous pollutants, to remove both gas and particulate simultaneously. What do you think? What is the right answer? What is the main purpose of gravity settler? Venkateshwara gave me a B answer. Can I expect more answers? Okay. Anyway, I'm agreeing with this. So this is to remove large. Yes. Priscilla also gave me B. Yes. So the thing is, because in the gravity settler, we are just taking the help from the gravity, so that and we are giving the particulate matter or air some time, so it can settle down under the effect of gravity. Okay, so in that way, because this is kind of passive, we are not using any energy. So this is crude way by which we can remove the particulate matter. But the thing is, because we are just taking the help of gravity, so only particulate matter the size of which are larger, that can only be settled down. Okay, because we are not using any charge, we are not using any chemical into that, so we can just remove or deposit large size particulate matter. So this is how it can be used just to settle large abrasive particles, and that have size more than 50 microns. And let me show you again the gravity settler. So this is something, so we are just giving some time. So how much time it will take? So we will talk about this as well. So we are just giving time so that under the influence of gravity, the dust can be collected. Okay, and the clean gas will go out. uh, so this is how it will work. And the advanced version of this gravity settler is that we are placing some tray one above to each other, so that the efficiency of your gravity settler can be increased. We will also talk about this, but the thing is, we can place tray one above the another, so that the efficiency can be increased. Okay, which of the following is true about gravity settler? And we have four options here. They are highly efficient for fine dust collection. They require high maintenance and are complex. They are simple device with low maintenance but low efficiency. They use electrostatic force for separation. We already have talked about thing. I don't think that there should be any problem solving that question. Priscilla gave me a C answer. Okay, so yes, C answer is the right one. So, highly efficient? No, this is not highly efficient because we are just relying on the gravity. High maintenance and are complex? No, this is very simple. Gas is coming in, then taking some time so that particulate matter can settle down, and then gas is going out. So this is very simple. So this is very simple, that have very low maintenance, and efficiency is also low. For the electrostatic, whenever we are using electrostatic forces, then this is electrostatic precipitator, ESP. So we have another instrument, ESP, that we will use. So in the gravity center, we are not using the electrostatic force. So that's how C answer is only the right answer here. Next question is, gravity settler are generally used as final cleaning device for high efficiency application, pre-cleaner before advanced device like ESP or fabric filter, for removing gaseous pollutant like NOx and SOx, as wet scrubber in chemical plants. This is again very simple. So I think you can give me the answer. Venkateshwara gave me a B answer. Yes, the answer is B only. So final cleaning device? No, this is not final cleaning device. Why? Because gravity settler is only used for the particulate matter, the size of which is very larger. But what will happen if you want to remove particulate matter that have very smaller size? So this is not our final cleaning device, but this is pre-cleaner, because whenever we will use ESP or fabric filter, that can be degraded. So just to prevent the efficiency of ESP and fabric filter, and to increase the life cycle of such kind of instrument, we do use gravity settler as a pre-cleaner. For removing gaseous, no, this is just for the particulate matter. As wet scrubber, no, we are not using any chemical in the gravity settler. So B is the right answer. Okay, now we will talk little bit about some technical thing about the gravity settlers. So in horizontal flow settling chamber, the design equation relating chamber length L gas velocity v, chamber height h, and terminal settling velocity vt. So you have to tell me the equation where we do have L, V, H, and VT. Little technical, but we will try to solve this also. Any guess about this? Something. Venkateshwara gave me A answer. Okay, so let's see. Yes, A is the right answer. That is L upon V is equal to H upon VT. But I will explain why this is just the right answer, why these are not the right answer. So we will talk little bit about the technical or engineering part of gravity settler. Okay. If you have any problem, you can let me know. Then I will try to explain you. So again, we are coming up with the same figure. So the gas will come in under the gravity, the dust will be deposited at the bottom, and gas will go out. Okay, the thing is, we have, this is our horizontal distance. So this is your L, right? And this is our vertical distance. So this is H. And then we have the velocity of gas. So this is your V. Okay, then a new term that we have is the settling velocity. So how much velocity we have so that the gas can be settled. Okay, so just keep in mind that we have two type of time. So we have time, right? If we are talking about time, then you just tell me the time to travel horizontal. So we have two type of time, the time to travel horizontal and time to travel vertical. Okay, so this is your vertical, this is your horizontal. So we have time for the horizontal flow or horizontal moving, and we have time for the vertical moving, so from up to down. So can you tell me, for the deposition, which of the time should be lower, V time or H time? Can you think about this? V time. So Venkateshwara told me that vertical time should be less. It means uh, if it is going with like it is taking 10 seconds to move from this L1 to L2, then to move from here, let's say this is H1 and H1, and this is, let's say, H node, and this is taking just 5 seconds. It means to deposit any particulate matter, this vertical time should be less. Otherwise, what will happen if it is taking more time? If it, let's say, if it is taking 15 seconds, then what will happen? Then the gas, this gas with the particulate matter will go out. Okay, that will not be deposited. So for the deposition, we should have vertical time that should be lower to the horizontal time. Okay, then can you tell me the formula of time? This is like fifth class or sixth class standard formula for the time in the relation of distance and speed. Can you tell me what is the formula of time? What is the formula of time?
V is equal to
Are you writing or typing something, or like I'm just waiting?
V is equal to D by T, ma'am.
Okay, so you people are not writing, but let me tell you,
V
we
is equal
people
to
know
D by
that
T.
speed is meter per second, right? So let me remove this first. So v velocity is equal to distance upon time. distance upon time. So time will be equal to d upon v. Okay, so if we are talking about horizontal time, then horizontal time means distance here will be L, and here velocity of air, so this will be v. If we are talking about the vertical timing, then this will be h, and here it will be terminal velocity, that is vt. And we know that the time of this should be lower, right? So at should be lower, or it can be equal to, okay, but it can't be larger. Okay, so this is what has been asked. The thing is, it can be equal, in equal settling will be happened, but if your horizontal vertical velocity is larger, then vertical time is larger, then it is not possible for us to collect the dust under the influence of gravity. Okay, so based on that equation only, we had the equation. So let me show you again. So this one. So I think this is clear now, because this is time, right? This is your horizontal time, this is your vertical time, and your horizontal time, vertical time should be lesser or equal to. So based on that, A is the right answer. Okay. Then if we do have so in the gas, so this is gas, and gas have some particulate matter. Okay. So so each of these particulate matter have some force, okay, that is coming from the down, that is coming from up. So we have to tell the resultant force that is acting on the particular particle settling in the fluid is given by g is for the J is for the gravity, B is for the buoyancy, and D is for the drag. Drag force, buoyancy force, and gravity force. So, can you tell me the resultant force that will act on the particle that is settling in the fluid? And this here fluid is nothing but the air. Little technical, but I think this is very interesting. So, for example, this is your any particulate matter, and some forces will happen on this. Venkateshwara gave me B, maybe, right? Or B, maybe. Anyway, so yes, B is the right answer. So, if you have any particulate matter, so let's say it is a spherical. Okay, so what kind of forces we may have? So, there may be force due to gravity. So this is Fg. Okay. Opposite to it, we may have buoyancy force, right? If you know that, if like if we are throwing something on in the water, so that will go up also. So this is because of that thrust or the buoyancy that will give you the opposite force. So opposite force will be force due to buoyancy. Okay, then another we have the drag force. So this drag force is resisting the movement, and here what we are doing, this is the particle that is settling in the liquid, so it means it is going down. Okay, and drag force is the one that will resist your motion, so that will also go in up. So this is your Fd. Okay, so it means if we are having the resultant force, so this resultant force will be equal to Fg, then minus these forces. Okay, so this will be Fd and minus Fb. So this is how this will be the resultant force that will act on your particle that is settling in the liquid. So that's how this is giving you the right explanation, B1. I think I also have some figure to show this. I think this is what I already discussed. So this is the gravity that is down, buoyancy up, and resisting the motion, drag force. So this is drag force, buoyancy, gravity. The resultant force will be gravity for force related to gravity minus force due to buoyancy and force due to drag. Okay, so this is how we can tell the resultant force on your particulate matter. Okay, so next question is, because we were talking about the drag force, right? So FD or F, you can also write FR. So can you tell me the formula of your drag force? Drag force is against the motion. So whenever there is something moving, then there will be some force that will resist that motion. So that will be the drag force, or you can say it is the inertial regime. So because of inertia, it is resisting the motion. So can you tell me what is the right formula for the drag force? Okay, maybe C, not correct. You can change your answer. You have full freedom that you can change your answer as many as time you want. Okay, so if we are talking about the drag force, then B is the right answer. It is A K C D. Yes, Priscilla gave me right answer. So A is the area. A is the area, and as I told you, drag force is just opposing the motion, so it is also related to your kinetic force, right? So, or kinetic energy. So here this is the kinetic term, and this is your drag coefficient. Okay, so Fr, or the drag force, will be equal to area multiplied by kinetic force multiplied by drag coefficient. So that's how B answer is the right one. Here also you can see drag coefficient, characteristic area of the system, and characteristic kinetic energy per unit volume. Okay, now we are diving into drag force, and as I told you, drag force is uh, A multiplied by K multiplied by CD, right? Now, can you tell me the formula of this A and K? So, in the drag equation, the characteristic area and kinetic energy per unit volume are uh, pi d square upon 4, K is equal to 1 by 2 rho Vt square, and likewise, we do have different options. Can you guess which one is the right answer? Mm, not B. Can you tell me if we do have kinetic energy, then what is the formula of that kinetic energy? Something 1 by 2 mv square, something like that. And if we are talking about the area of spherical, then it is pi r square. So can you like do some combination, and we can derive something out of these formula, 1 by 2 mv square and pi r square, and then can we have some formula within that options? Okay, Priscilla gave me A, and Venkateshwara, I will correct you, don't worry about this, but A is the right answer. Okay, because we are talking about spherical thing, right? So spherical means we are talking about circle. So if we do have pi r square, area is pi r square, but in place of this r we are using diameter. So diameter is, so what is the relation between radius and diameter? That radius is equal to d by 2, and d by 2 pi r square means d by 2 square multiplied by pi, right? So this will be pi d square upon 4. So this one is the right answer for the area. Then we have uh, kinetic energy. So we know that kinetic energy is equal to 1 by 2 mv square, that we learned in our physics class uh, in our school time, right? Ki kinetic energy is equal to 1 by 2 mv square. But here we are using kinetic energy per unit volume, so we are dividing it with the volume. So m upon v, mass upon volume is density, right? So this will be 1 by 2 rho v square. So this is something we were talking about. So that's how A answer is the right one. Drag force have area. Area will be, because it is spherical, then we have to take the circle area. And kinetic energy, we know that 1 by 2 mv square. But if it is per unit volume, then m upon v will give you the density. So this is how A answer is the right one. Okay. So this we already have learned. Okay, now we are moving for the derivation of terminal settling velocity. Okay, we talked about the velocity with which air is coming in and out. Okay, but what velocity we need so that the particulate matter can be settled down? And if we are talking about the terminal velocity, so this is again the physics word that we have learned in up to 12th standard, that when something will fall on that surface, then initially there will be some acceleration. uh, Priscilla already gave me B with the question mark. uh, Venkateshwar also gave me B. Yes, B is the right answer. uh, Let me tell you. Yes, so we want to derive this. Okay, and we can derive it very easily, don't worry about this. But first we have to talk about this terminal settling velocity. So if something is falling from sky to on the surface of our earth, so what will happen? Initially there will be acceleration. Okay, means velocity is increasing with the time, but there will be one stage will come where the acceleration due to gravity will be zero. Okay, acceleration due to gravity will be zero. So at that moment, that velocity will be known as the terminal velocity. Okay, so it means if we are talking about the acceleration, the force due to gravity, that is ma, this will be equal to zero whenever we are talking about the terminal settling velocity, because here acceleration will be zero. This is the condition to be known as the terminal velocity, that there will be very constant velocity with which the object will fall from sky to the surface. There should not be any acceleration. That time only the velocity will be known as the terminal. So it means what we are saying here, fg will be equal to 0. Okay, now I will tell you how this was derived. We are going back to this one. We have learned this one, right? Resultant force is equal to Fg, uh, force due to gravity, minus buoyancy minus drag force. We have learned the formula of this drag force. Then we also have formula for the buoyancy, and this will be 0, right? Because we are talking about the Vt. Okay, so what will happen? Ma, that is uh, resultant force, is equal to mg. So this is mg. Then force due to buoyancy, this will be defined as this one, and then fr. Okay, but what we were talking, this will be equal to 0. Okay, because uh, there should not be any acceleration due to gravity, so this will be 0. So it means fr fr will be equal to this term. Fr will be equal to this term, and this is how we are doing some reshuffling into that. And then we people know that F is equal to AKCD, and we also know about this formula. If we are putting this, then we will get this equation. I think little trickier, but very simple, that we have some resultant force, and then what we are doing here, because acceleration will be 0, then we are equating the things. So here we are equating that Fg is equal to Fb, uh, Fb and Fd, and this is how we are putting all the equation into that, so that we will have this one. So what is this? This 4, this is g. This is g is gravity due to acceleration. We know that this is 9.8. Then we have dp, that is the diameter of your particle. This is the density of your particle. This is the density of the gas, and cd is the drag coefficient, and rho g is the density of your gas. So this is how we can derive the things. If you have any problem, you can let me know, but so this is very important. This is every time we have to see what velocity, what terminal velocity we should have. So engineering people are working very hard to maintain that terminal velocity, so that there should be the deposition of dust due to gravity. Okay, so the now question is, why is terminal settling velocity important in air pollution control device such as gravity settlers? It determines the heating rate of gas. It defines the velocity at which particle remains suspended forever. It indicates the constant velocity at which particles settle, helping design equipment size and efficiency. It has no effect on particulate separation. I think very simple. Why terminal settling velocity is very important, why we derive that equation, what was the need for that. Okay, Venkateshwara gave me answer C. Yes, obviously. So this is the constant velocity. As I told you, there should not be any acceleration. Okay, so a is equal to 0. So it means the resultant force that we will have ma, that ma will equal to 0. Okay, then we will have fg, and then we will have fd, drag force, and fb. But the resultant, and this is minus minus, and this will be equal to 0, because the acceleration is 0, because velocity is constant. And from there only, here we know that this is mg. Here we know that for the drag force it is a k c d. Then for the drag force we also have some formula. Then if we are putting every formula into that equation, then we will have the uh, settling velocity. But this is constant velocity, and that's how it will help us to design uh, for what particular size, what kind of efficiency we may attain. Okay, so that's how C is the right answer. Okay, the overall collection efficiency of a gravity settler is defined as ratio of particle diameter to chamber length, ratio of weight of material collected to the total amount entering collector multiply by 100, fraction of gas molecule absorbed per unit chamber volume, terminal velocity divided by gas velocity multiply by 100. If you want to calculate the overall collection efficiency, then what it would be? Any guess? Not D. You can change your option. So, if we are talking about the collection efficiency, it means how much particulate matter came in and how much has been deposited. So, the fraction or the ratio of this will give you the collection efficiency. Yes. So, answer will be B. So you have to weight the material that has been collected at the bottom due to gravity and the total amount of particulate matter that entered into that collector. So and multiply by 100 will give you the collection efficiency. Okay, the next question is, we have fractional efficiency in the ith size range is given by. So what it is because it is not like that we have just two, let's say 2 micrometer diameter particle, we may have 3 micrometer diameter sized particle, we may have 10 micrometer as well. So we have variety of size of each particulate matter. Okay, and as I told you that efficiency to remove the particulate matter is depend on the size of the particulate matter. Okay, so it means for each particle size we may have different efficiency, and this is something known as the fractional efficiency of the ith size range is given by, then what it will be. Venkateshwara gave me B with the confidence. Then yes, B is the right answer. It means, so let's say if we are talking about 2 micrometer sized particle, then how much of this has been collected? So what is the weight of that particular sized uh, particulate matter, and what was the total weight of that particular particulate matter that entered into the collector? So this is how for each size we will have uh, the collected weight and the total entering weight. So this is how it will give you this ratio will be known as the fractional efficiency. Here also you can see as we are increasing the particle diameter. Okay, this is in micrometer, so efficiency is increasing. So efficiency will be near to 100% when the particulate size will be 50 micrometer. It means for each particulate matter size we have some efficiency, right? So this is something like that. Okay, from the collection efficiency curve that I showed you right now, which particles are removed with highest efficiency in gravity settler? Very fine particle, medium particle, coarse particle, or particle equally? Priscilla gave me answer C, and Venkateshwara also gave me a yes. So this is C. Whenever we will have the particle size is large, it means there would be the gravity that will drag that particulate matter to the bottom or on the surface. So this is whenever we do have large size, it means more collection efficiency. And here you can see if we have dust size 5, or 5 to 10, 10 to so this is your size and this is your efficiency. So you can just see the efficiency will increase whenever the dust size will increase. Okay. Okay, the overall collection efficiency of a gravity settler is also calculated as, so this is the total collection efficiency and you have to tell me total weight of gas upon total volume of chamber, and the summation of wi and the fractional efficiency, and v upon vt into 100, h upon l into 100. Venkateshwara gave me B answer. Yes. So the answer is B. This is WI. WI is the weight fraction in each size range. It means out of, let's say, 100 gram of 2 micrometer, how much has been collected? Let's say it is collected 4 gram. So this will be 4 upon 100. Okay, so and the efficiency, what was that efficiency? Then this will be ni. So based on that you can calculate. So just see here, I think I also have numerical on. Okay, so let's say this is your weight that has been collected, 2 out of 100 gram, 2 out of 100 gram for, and we also have given fractional efficiency. So based on that, can you calculate the total collection efficiency? So what it will be? 2 multiplied by 1 plus 2 multiplied by 7 plus, and this is how up to this one, and this will give you the fractional efficiency. So just see here, this is how we can calculate the total fractional efficiency. Okay. Why does inerting several trays in the gravity settler improve collection efficiency? As I told you initially, it is just like this one. But what if we are having some trays in our collector, gravity settler? Then why we are inserting several tray in the gravity settler? We have four options here. Because trays reduce gas flow velocity inside the chamber, because particle have shorter distance to fall below reaching a surface while gas velocity remain the same, because tray increase turbulence which trap all particle, because trays completely stop the gas flow forcing particle to settle. Hmm, I'm getting a wrong answer from Priscilla and Venkateshwara, because you people gave me A answer, but I want different answer. I will tell you why. Okay, Priscilla changed the answer from A to B. I'm also agree with B answer. I will tell you why. Because we are inserting it. So, for example, if you are just inserting it this in this that way, so the velocity of the gas will not be changed. So V will be same. Okay, but as I told you, now in a initial MCQ here, it was H upon VT and one was L upon V. So this Vt is the terminal velocity and this is the velocity of your gas. This is your length of the chamber and this is your height of the chamber. Okay, so whenever we have height of the chamber will be reduced. Why reducing? Because here this is just H, this is again another H, again this is another H. So it means we have reduced our total H, uh, or let's say dash H is equal to 1 by third of H. So what we are doing, we are reducing this. What will happen if we will reduce this? then the time to settle down will also reduce. Time for the settling will also be reduced because it is directly proportional, because time to settle is equal to our vertical distance upon velocity, settling velocity. If we are reducing this h, it means we also reducing the settling time. Okay, so this was just the right answer. So particle have the shorter distance to fall before reaching the surface, while gas velocity will remain the same. Okay, so here what we are just doing, we are reducing the time of the time with which it will fall down. Okay, so that's how B is the right answer. Because tray reduce gas flow velocity inside the chamber. No, the velocity of the gas will be same, but we are doing some manipulation in the settling velocity because we are reducing the time. Okay, so that's how B is the right answer. So just see here, initially it was H, but here if we are inserting some trace, then this will be uh, del H, right? So inserting several trays, the collection efficiency of the device is improved since the gas flow in the velocity chamber remains substantially same, yet each particle have much shorter distance to fall before reaching the bottom of the passage. Okay, these are some that I will not derive. So, if we have hydraulic diameter, that is dH, for the flow passes between trays in the gravity settler that have the width of W, and the tray spacing is del H, then how you will define the hydraulic diameter? Because I'm not deriving this, and this is just to mug up, so I'm not taking much time to show you the answer. Venkateshwara also gave me right answer, that is B. So this will be 2W del H upon W plus del H. You can read about this thing. The next is the velocity of gas flow in the chamber, and that chamber have the volumetric flow rate Q and width W, number of trays N, and the tray spacing is del H. So can you tell me the velocity of gas flow? So the thing is, if we are talking about the flow rate, so the unit of flow rate is meter cube per second. Okay, so and meter cube per second means meter square upon meter upon second. So this is something equal to meter square multiply by, because it is meter per second, then this is velocity. Okay, meter square is nothing but the area. So you can say that q is equal to a multiplied by v, and you know that area will be equal to, because this is rectangular, then area will be uh, L or length. So width here will be W into del H. Okay, and so can you tell me now the right answer? As I told you, flow rate will be in meter cube per second. So by which we got to know that the flow rate will be equal to area upon velocity, and the area of the rectangle will be length into breadth. So this will be W multiplied by del H, and we have V, and we have number of trays, that is the N. So can you now tell me the right answer that will define? Venkateshwara gave me answer B, Let me see. Yes, so this is giving me right answer, that is V is equal to Q upon N W delta H, because here we do have n number of trays, so we also have to consider this one. It's all right. And these are not the right answer, because here we do not have area. And this is because we have to have it divided with the number of trays, so that's how n will be in the denominator. Okay, the next question is, as I told you, we do have a lot of trays, and that tray have the height delta H, right? Each tray have the height delta H. But what will happen if we have some dust on it? So if there is a thickness of dust, that is Hz. So let's say this is the thickness of your dust and this is known as Hd. That will form a layer on the tray. Then the effective spacing will be what? But we are talking about del H. You are very nearby, but not the right answer, Priscilla. But it is very clear that you have to subtract, right? Venkateshwar also gave me wrong answer. Yes. So the answer will be B. So why there is a B? As I told you, no. Let's say we have this is total height of your gravity chamber, and that is, let's say, 10 meter. And if we do have 5 trays, then your del H will be H upon N. H upon N. So it will be like, for each tray we will have height of 2 meter, because total height is 10 meter. We have 5 trays, then each of height of like in each tray will be 2. So this will be H upon N. Initially it was H plus H upon N, but as I told you, there is a deposition of the dust, and let's say this is the deposition, then we have to subtract this, because now the height is lesser. And how much lesser? We have to subtract this much. Okay, so that's how minus HT. So this is how B answer will be the right one. Okay, so I think about gravity settler, everything is very clear. Now we are moving to the electrostatic precipitator. And as I told you, if we do have positive negative charge, then there will be neutralization. Neutralization means collection will be easier for us. Okay, so such kind of instrument we also have, by which we can remove the particulate matter. So now let's have some question on ESP. Little bit lengthy MCQ, but I think that will be easier for you to solve. So we do have two type of precipitator, ESP precipitation. One is the parallel plate precipitator and another is wire and pipe precipitator. And you have to tell me the difference between these two type of precipitator. So you just read, because the text is so long, so I don't want to read. Little lazy. So can you tell me the right answer? You can take your time. Priscilla, A with a question mark. It can be. Okay. So yes, A is the right answer. That whenever we have parallel plate precipitator, then okay, let me show you before giving you text. So these are two type of precipitator we have. This is the parallel plate and this is your wire and pipe precipitator. In parallel plate, what we have, we do have parallel plate. These are our parallel plate that will collect that is also known as the collecting electrode plate. Okay, then we have these are our diode, discharge, electrode rod, these two, and the gas will come in from this part and will go out from this part. And this one have the positive charge, and here we have the negative charge in the discharge electrode rod. So this is how there will be the neutralization and collection of the particulate matter will happen. If there is wire and pipe respirator, it means we are having a pipe, and in that pipe we have a wire. So this is our discharge electrode and this is our pipe. So pipe have positive and this has the negative. And whenever the gas will come in, a particulate matter will take the negative charge. Whenever this negative charge will collide with this outer layer, then it will neutralize, and this is how collection will be done. So this is wire and pipe pressure. Now coming to the options that we had. So in parallel plate respirator, discharge electrode are thin wire placed between parallel grounded plates, while wire and pipe respirator discharge wire are located inside the cylindrical grounded pipe. And that's what I showed you. I'm skipping this one. Okay, so again we are having some technical term. And in tubular, so this tubular is cylindrical type that we talked about. In that we have area upon volume ratio. So this you have to tell me this ratio how we can express it. So we have 2 upon s, 1 by dc, 4 by dc, and 1 by 2s. Okay, because you people do not know what do you mean by S and DC. So let me give you quickly the answer first. So here answer will be 4 upon DC, and let me show you how. So if we are talking about tubular, it means we have pipe and wire. So this is cylindrical. So here what we will have, the surface area will be pi DCL. Okay, so and D here is the diameter and L is the length. So I think in the cylinder, the area of the cylinder. So this will be pi DCL. Then volume here will be pi DC square upon 4L. And if we want to calculate the ratio of this AC upon V, then this we will get 4 upon DC. It means because this is cylindrical tube, then we are also considering DC. So that's how 4 by DC will give you the right answer. Now the another question is on plate type electrostatic respirator, and here if you want to calculate the area upon volume ratio, then how you will calculate? It means the diameter will not play any role here, because we are not talking about cylindrical. So this will not among the right answer. This will not among the right answer. So now you have answer 2 by S and 1 by S. And because right now I don't think that you know about S, then sorry. Let me give you the answer for this. So here S is the distance between these two parallel plate. Okay, and here length is L and height is H. So the surface area will be 2HL, because we do have two collecting plates, and because the area is length into breadth. And the volume between the plates will be HLS, and this is how it will give you 2 by S. Okay, so if we want to calculate the efficiency of ESP, electrostatic respirator, in the term of drift velocity. So because here the gas will come in and out, and so here there is the velocity that is known as the drift velocity, and we have area collection area AC, that we already have talked about this, and volumetric flow rate, the rate with which air is coming in and out. So this will be the flow rate. So based on these terms, can we define the efficiency of ESP? So what it will be? We have four options. So can you tell me the right option for calculation of efficiency of ESP, electrostatic precipitator? Because we do not have derivation here, then you just have to learn, because there are some numerical question on this. uh, Venkateshwara gave me D, but not D. This is B. So here there is the exponent term also here, because you will see for ESP, the area, to increase the efficiency, we have to increase the area exponentially. Okay, so it means if we want to increase the efficiency, let's say from 90 to, let's say, 95, then we have to increase the area exponentially. It means we need a very large space for the electrostatic precipitator to launch at any place. And this is very important for us. To increase any efficiency, we need to increase a lot of area. Okay, so this is a little disadvantage of ESP, but the advantage is, it can collect particulate matter at a very low sorry, at a very low size of particulate matter. So just keep in mind that the first thing is, there is a relation between efficiency and area. This is exponential relation, and this will be 1 minus. So this is how B answer will give you the right option. So here you can say, this is 1 by 1 minus exponential minus VPM AC upon Q, and we already have learned about these things. Okay, this was for electrostatic precipitator, the important thing was that you just need to know the principle. What is the principle, how this electrostatic precipitator works? And the second is the efficiency. Okay, I think I have one numerical at the end related to this ESP efficiency that we'll talk about. But before that, we will talk about the fabric filter, right? So we have talked about gravity settler and ESP. Now we are coming to fabric filters. Fabric means the filter that is made up of the cloths. Okay, and because we know that each of the cloth are woven, it means the threads are like this. It means there is some space, right? And whenever the gas will go in and then out of that woven thread or woven fabric, then the particulate matter will be collected in that space. So that's how the fabric filter will work. And we have very simple question on this. Fabric filter are widely used because of their very high collection efficiency. The efficiency of fabric filter is typically 70 to 80%, 85 to 90%, more than 99.9%, 60 to 75%. What do you think? What is the efficiency? Priscilla gave me answer C. Then yes, because we talked about very high collection efficiency. So very high means the efficiency of fabric filter is more than 99.9%. So yes, C is the right answer. This is something fabric filter I was talking about. So this is your fabric filter, and this is something bag like fabric filter. So it means, and because you know that the fabric is woven, so whenever there will be gas, that gas will be that gas will have the particulate matter. That particulate matter will be deposited into these bags, and then gas will come out. So we have thousand of such kind of bag in a single machinery, right? And this is how this filter bags, or this is also known as the bag house filter. So this is how we can collect a lot of particulate matter into such bags of the made up of fabric, right? So this is something we were talking about, fabric filters. And because we are installing thousands of such bags, so that's how the efficiency is very high. Next question is, fabric filters can effectively capture particle in the size range of 10 to 100 micrometer, 1 to 10 micrometer, 0.01 to 1 micrometer, and less than 0.001 micrometer. Venkatesha gave me A and then Priscilla C. C is the right answer. As I told you, the efficiency of this is very high. And for the like, if we are talking about settler, gravity settler, GV, here the 90%, 100% of efficiency can be achieved when the size is near to 60 to 70 micrometer. If gravity settler, very simple, machinery can give you near to 100% efficiency at the range of 60 to 70 micrometer particle size, then just see, if I'm saying that fabric filter is very efficient, it means this should not be the answer, right? And so the range for the effectively capturing the particle, so the range is 0.01 to 1 micrometer. But there is some limitation of fabric filter also, and you have to tell me the major limitation. They generate excessive noise, they cannot operate in a moist environment, they cannot handle high particle concentration, they cannot clean once clogged. What do you think? What is the major limitation of fabric filter? They cannot handle high particle concentration. No, they can handle high particle concentration. Because as I told you, now we are installing thousands of such bag filters made up of fabric. So it means they can have a very high load. So they can handle high particle concentration. So C is not the major limitation. Okay, Venkateshwar now changed to B, and yes, I agree with B. Priscilla also gave me B. They cannot operate in the moist environment. Why they can't operate in the moist environment? Because it is, as I told you, now this is fabric, and fabric is woven. So whenever the gas have some moisture, it means the particulate matter will clog these pores and will not be deposit at the bottom then. So so this is how this will reduce the efficiency of your fabric filter. But we can clean these once they are clogged. But the thing is, whenever we will have the moist environment, it means at each minute, or within 5 minutes or 10 minutes, the fabric filter will be clogged. Then the cleaning repetitively will be very difficult for us. No doubt we can clean, but here the cleaning procedure will be very lengthy. Okay, so that's how we can't operate in the moist environment. So, okay, the thing is, we do have fabric filters, right? So that we can deposit particulate matter. And we also have air purifiers. You have heard that in Delhi, most of the people right now in houses are using air purifier. So there are some differences and some similarity into fabric filter and air purifier. I think we have some question and we will solve that also. uh, the important design parameter of fabric filter is, now we are talking about the technical thing about the fabric filter. So can you tell me the most important design parameter of fabric filter? Temperature of inlet gas, pressure drop across the filter, air or gas to cloth ratio, flow velocity of particles. Which is the most important design parameter we should have before designing the filter, fabric filter? Okay, so I'm getting a B answer from Venkateshwara. Pressure drop across the filter. You can correct. You can give me another option. Then I will say, okay, this is the right answer. But B is not the right one. And the important parameter is air to cloth ratio. So as I will talk about this, I think in the next slide I have. But temperature of the inlet gas, yes, it is important, no doubt, because it can give you the combustion or corrosion of your fabric, but not most important. Pressure drop is also important, but not that much important, as it is the air to cloth ratio. How much air is coming, so the velocity and the area of your cloth. So this is very important to design any fabric filter. Flow velocity of parameter, this is again important, but the most important is gas to cloth ratio. So the velocity of gas and the area of your cloth. So this is very important for us. Okay, so which feature distinguishes fabric filter from HEPA filter? So HEPA filter, as I told you, there is some similarity and dissimilarity in air filter, air purifier. So this HEPA is a type of air purifier. So what difference we may have in fabric filter and HEPA filters? High efficiency, ability to renew the filtering surface periodically by cleaning, operation at high temperature, use of borosilicate microfibers. Venkateshwara gave me a B answer. Yes. So this is the answer, that if we do have fabric filter, then we can renew the filtering surface area by cleaning it with the time. But in HEPA, we can't do this, because here the filter is not made up of fabric, but these are borosilicate microfiber. So that's how for the fabric filter it is easier for us to renew it by cleaning that filter. But HEPA is made up of borosilicate, then we can't renew it, right? So I have some explanation here. So the major operating feature of fabric filter that distinguishes them from other gas filter like HEPA is the ability to renew the filtering surface periodically by cleaning. And full form of HPA, just see, high efficiency particulate air filter. And here the media is usually made up with borosilicate microfiber that have the diameter from 200 nanometer. Okay, again, we are talking something technical about the fabric filter. Okay, you have to understand, whenever we do have fabric, right? This is our fabric. Then, and if we do have some particulate matter, okay, so how that particulate matter can be deposited into these things? So we have three mechanism here. The first thing is we have these particles, and so there may be diffusion, and then inertial impact, and we will talk about one more, interception. So we will talk about this, but the thing is, if we do have the inertial impaction, it means there is fiber, and the gas will, whenever we do have the particle matter that have very smaller size, then there will be inertial impact. Okay, and here the efficiency will depend on some parameters. So can you tell me which parameter? And now we have some new terminologies: only Packlet number, collision factor and adherence factor, uh, Kuwabara hydrodynamic factor, and fiber porosity alone. I think here we do have a little new terminologies, so I will not expect that you will give me right answer. Venkateshwara gave me C, but the answer is collision factor and adherence factor. Yes, Priscilla gave me right. And let me show you how. Okay, so here what I wanted to show you. So if this is our collector, or let's say fiber, and the gas is coming, that gas have some particles. Okay, that particle may have may be collected due to inertial impaction whenever the size of this is small. Okay, when the size is large, then this collector may have contact with particulate matter, and this is how this will be the part of interception. Then another is diffusion. Diffusion is, okay, the size, whenever the particulate size is very small. Can you see? Very small, smaller than this inertial. Okay, so here the size is not small, but you can say larger. Sorry for the misinterpretation. But here for the inertial we have larger size, but for the diffusion we have very small size. So in that case, whatever the streamline flow we have, that streamline flow path will not be followed by this. So this, there will be another terminology that will be the diffusion. So because of the diffusion, that there is a higher chance that fabric can be interact with these particulate matters, because these are not following such path, these are not following such paths, because there is a smaller size, there is a Brownian movement, if you have heard about this. And because of this Brownian movement, there is a chance that there is a collision between collector and the particulate matter. So this will be the part of diffusion. Interception, we already have talked. If we have medium size particulate matter, that will make some connection with the collector, so this will be the interception. And if due to inertia, inertia will happen only when your particular size will be larger. Okay, so inertia will resist the movement of this particulate matter with the gas. So this is how it will be resisted, and it will go down and it will be collected. So the thing is, whenever we are talking about fabric filter, so these three mechanism, interception, inertial impaction, and the diffusion will play very important role. And because we were talking about inertial impaction, so here the and collision and adherence factor will play very important role. Okay, here also you can see uh, these are the three mechanism. And in that three mechanism, if we are talking about inertial, then particulate size will be more than 1 micrometer. For the interception, the particulate size will be 0.1 to 1 micrometer, and for the diffusion, particulate size will be very less. And here it will be due to inertia, here it is due to the streamline following, and then there will be the interception, and here it is due to the Brownian motion. So this is how okay. And the description is, I think, very important right now. because here the size is very large, then there will be some inertia that will resist the streamline flow, and this is how it will hit the filter. If we are talking about the interception, it means it is following the air path, the particle is following the air path, but it will touch the fiber. And diffusion, it will not follow the streamline because there is the random motion due to its smaller size. So based on that three mechanism, fabric filter is very efficient in collecting the particulate matter. Okay, for particle with less inertia, okay, separation in fabric filter mainly occur through Brownian motion, direct interception, gravitational settling, diffusion. The particle that do not have much inertia, it means that particle is uh, little smaller in size, then the separation in fabric filter may occur due to any guesses. So I'm canceling out two options. Gravitational settling, because we are talking about smaller size, because it has the less inertia, so it means we are talking about very smaller size particle, and that smaller size particle, the efficiency for the settling is not much higher, so this is not the right answer. Then we have Brownian motion, direct interception, and diffusion. Brownian motion is the part of diffusion, as I already have talked. Then, okay, Venkateshwara gave me B answer, that is interception. Yes, I agree with this. So, interception will be the main mechanism by which we can deposit the particulate matter. Now, which statement about direct interception is correct? We are talking about interception. It is dominant for particles smaller than zero point 0.1 micrometer. It occurs when a particle collides with a fiber due to its inertia. It is significant when particle diameter is comparable to filter diameter, and it depends only on particle density. What do you think? As I already have discussed about the interception, about the diffusion, and about uh, the inertial impact, then based on that, I think you can give me the right answer. Priscilla gave me a C answer. Yes, I also agree with C, because if it is particular is smaller, a particle is smaller than zero point 0.1, then here we will talk about diffusion. Okay, if it occur due to inertia, then we will call about this inertial impact. And on particle density, no, nothing is depend on particle density, but it is the particle size. Okay, so this is again not the right answer, so the right answer only will be C. Okay, so the next is the diffusion mechanism of particle capture in fabric filter is important for. Now we are talking about diffusion mechanism. Particle larger than 10, around 1, submicron particle, and all size equally. Venkateshwar and Priscilla with C. Yes, we already have talked. Whenever there is the Brownian moment, then it will not follow the streamline. So it means there is some and there will be some collision with the collector just because of the Browning moment. And Browning moment will only happen whenever the particle size in the submicron. So C is the right answer. Okay, we have efficiency due to diffusion, due to interception, due to inertial impaction. So if we are talking about the diffusion collection efficiency, then it will depend on what? Pecklet number and drag coefficient, only Kuwabara hydrodynamic factor, particle density and fiber porosity, Reynolds number only. Okay, so you both of you gave me A answer. Then yes, the answer will be Pecklet number and drag coefficient. We already have talked about the drag coefficient, and if we are talking about Pecklet number, so this is something related to the collection efficiency. So A will be the right answer. More than 99.9% collection efficiency in fabric filter occur for particle smaller than 0.01 micrometer by diffusion alone, larger than 1 micrometer through impaction plus interception, between zero point 0.1 to zero point 0.5 micrometer by Brownian motion by gravitational settling for all particle size. I get some answer. Priscilla gave me B answer. Of course, whenever we will have these three mechanisms simultaneously, then the efficiency will be increased, right? Yes. So B is the right answer. So whenever and whenever we are increasing the particle size, then obviously efficiency will increase. So whenever we have impact plus intercept and then size larger than 1 micrometer, then the efficiency will be very high. Okay, because we were talking about that efficiency of fiber filter, and the most important design parameter was air to cloth ratio. So, can you define that air to cloth ratio? Volume of dust collected per unit area of cloth, amount of area air flowing through each square foot of filter media per minute, pressure drop across the fabric filter ratio of fiber thickness to fiber diameter. Venkateshwar gave me B answer. Yes, so this is B answer. So this is amount of air in the form of let's say flow rate, and so how much area is flowing per unit foot of filter media per minute. So this will be known as air to cloth ratio. And as because we talked about fabric, right, so we can use different type of fabric to manufacture that fabric filter. For example, we can use cotton, we can use nylon, we can use dacron, we can use teflon. But you have to see the type of gas that you have, either it is acidic or basic in nature, either the temperature of your gas is higher or not. So based on that, you have to select a particular type of fabric. So for example, if you will see, if we are using cotton fabric, then if we do have the gas that is acidic in nature, then this will not work, because the relative resistant to attack by acid here is very poor. So we have to use either polyester or teflon. Okay, and based on temperature also, if the temperature of your air is higher, then you can't use cotton, because it can't resist the high temperature. So we have to use teflon. Okay, so but we also have to see the cost of it. So if we are using teflon, then it is very expensive. And likewise, we can also use glass, nylon, wool, but each have some limitation also. So based on what kind of gas that will flow through that filter, you need to determine which kind of filter you will use. And as I told you, air to cloth ratio, so this is amount of air flowing through each square feet of filter media each minute, and typically the value of it is between 1.5 to 3.5 meter per minute. And the concentration of dust loading will be V, that is the flow rate will be Q upon V is the concentration of gas loading, and Q is your flow rate, upon A is the area. So V is volume here in actual. Okay, so we have talked about fabric filter, electrostatic precipitator, and gravity settler. Then a few questions, just I think 3 or 4 questions. I think we have on cyclone separator. So in cyclone separator, what we are using is we do have something like cyclone. So we have outward force and we also have inward force. So based on that outward and inward force, and that would whenever your air will move spirally, then there will have some in the rotation, then there will be outward and inward force, and that will give you something about the collection of particulate matter in the cyclone. So in cyclone separator, the high speed rotating airflow create pressure gradient, centrifugal. Okay, you people already have given me a B answer. Then yes, outward force will be centrifugal, right? And inward centripetal, but centripetal have different characteristics that we will talk about. But because whenever the gas will move in a circular motion, then there will be outward force, centrifugal. So whenever your particulate matter will have the centrifugal force, that will make some contact with the outer layer, and outer if outer layer is have some charge, so that again will neutralize your charged particle, and that's how deposition can be happen. So this is the centrifugal force that separate particle from gas stream. So here you can see the gas will come in from your left hand side, then it will have outer vortex, then after depositing the dust it will have the inner vortex, and from that inner vortex this gas will leave, right? This is again the same representation. Okay, there is a one terminology in cyclone separator, that is cut point. So can you tell me what do you mean by cut point? The maximum particle size collected with 100% efficiency, the particle size removed from stream with 50% efficiency, the smallest particle that can pass through the dust collector, and design parameter diameter of the cyclone body. What do you think? What do you mean by cut point? Venkateshwara gave me C answer, and let me show you. So answer is B. Then this is the particle size removed from the stream that have 50% efficiency. So this will be known as a cut point. Okay, there is another terminology related to cyclone separator. So the for the particle to be separated in the cyclone, its diameter must be at least, and D node is the diameter of the top outlet. So because like whenever we are designing any of the instrument, then we have to take care of like what kind of what size of particle at least we should have, otherwise we will use the gravity settler or something like that. So okay, Priscilla gave me C with the question mark, but I will say it is A, that is zero point 0.1 D node. Okay. In cyclone separator, because we are talking about the outward force that will act on the particle, then you have to tell me either it is drag force or centrifugal force or gravitational force or pressure gradient force. It is outward force, and we are talking about the circle. And you know that for the outward, what kind of force we talk about. So this is centrifugal. Yes. So Priscilla gave me okay. Venkateshwar also gave me right answer. So whenever there is a motion, circular motion, so there is always centripetal and centrifugal force. Centripetal is force from inside, and centrifugal force is force outside, outside force that will act on any particle. So this is the centrifugal, and this is equal to mv square upon r. If we are talking about the inward force that will be opposite to the particle motion in the cyclone, this is due to what? Viscous drag from gas, centrifugal gravity settling, and electrostatic force. No, centrifugal force is for the outward. For the inward, this will be, yes, this will be a, that is the viscous drag force, because that is opposing the motion, and we already talked about that, na, resulting. So whenever there is a motion, so the force that will resist the motion will be your drag force. So the motion that is opposing the particle motion, so that will be an inward, so that will be your viscous. So here the viscous force will be equal to centrifugal force to move in the circle. So that's how A answer is the right one. I think this I already, right now only I discussed. At the equilibrium inside a cyclone separator, the condition between centrifugal and drag forces A, B, C, D. And as I already have discussed the formula of centrifugal force, so this was mv square upon r. And we already have talked about the drag force. It was AKCD. A was area, K was kinetic energy per volume, and CD was drag force. So based on that, A answer is the right one. Yes. And here also you can see for the centrifugal force, it is mv square upon r. For the drag force, it is 3 pi mu g dp vr. And, in equilibrium, these forces will balance to each other. Okay, so you have learnt about gravity settler, you have learnt about cyclone separator, ESP, and fabric filter. Now, the important question is you have to give me the sequence based on the efficiency from lowest to highest. Which one have the lowest efficiency, which one have the highest and the moderate? Priscilla gave me answer A. Okay. Yes, I also agree with A. Gravity settler have lowest efficiency. Then we have cyclone separator. Then high efficiency is for electrostatic precipitator, but the highest efficiency is for the fabric filter. So I think now this four instrument or the principle of this machinery is clear to all of you. Here you can also see for the gravity settling, efficiency is typically 50%, ESP it is 98, for fabric filter it is near to 99, and cyclone separator it is near to 90%. And here is also some remark how much area we need, what kinds of sensitivity we have to the environment or to some chemical attack. You can read about these things. At which particle size does diffusion become dominant mechanism in wet scrubber? Now we are talking about scrubbers, and as I told you, scrubbers are those which can remove both gas and particulate matter. And in wet scrubber also there is one diffusion mechanism. In the wet scrubber there is the diffusion mechanism, interception also works, and that inertia is also work. So both of you gave me C answer, then yes, a C answer is the right one. Then if the factory is emitting fine particulate matter of 2 micrometer size, which type of scrubber would be most efficient? Okay, so in scrubber we do have different type of scrubber. It can be spray tower, it can be centrifugal scrubber, or it can be venturi scrubber. Gravity settler is not the right answer because we are talking about smaller size. Then and we have to talk about scrubber only, so out of A, B and C will be the right answer. But if there is a fine particulate matter of 2 micrometer size, then the answer will be venturi scrubber. Spray in the spray tower, we are just using chemical that will spray, okay, on that gas. In the centrifugal, we also have that uh, cyclone separator also within that. So we have cyclone separator plus spray that will give you the centrifugal. And in venturi, we do have a bottleneck, so that will reduce the velocity, and that's how it will increase the efficiency. So for the fine particulate matter, so C is the right answer. So here you can see some difference, but I want to skip it because the time is out. There are some advantage and disadvantage of wet scrubber. So they can reduce the hazard of explosive dust air mixture, but because it will give you sludge, wet sludge, and that will create some problem. So this is disadvantage. You can read about this. Venturi scrubber is particular suitable whenever we have very sticky, flammable, or highly corrosive fine particle. Now I am not taking your answer because time is up and I have just 2 or 3 questions. If we are talking about packed bad scrubber, then again we will have the spray, but we also have some bed of stone and all that can also filter out the gas, and particulate matter can be collected. So that's how they create a large surface area for gas liquid contact. Yes. uh, if we are talking about the gas absorption, then we can use different type of absorption material or solvent. So the one that can involve both physical and chemical absorption is sulfinol. And adsorbent, we know that for the adsorbent, every time it is activated charcoal, that can work. Okay, so there is again, like we do have air purifier in the houses, and we have active and passive air purifier. If we do have active air purifier, that will release negative charge ion, and that's how it will deposit the particulate matter. And in the passive purifier, we will use filter that can just remove the pollutant. We do have air purifier. So if that will work on the air, the force air that will trap the pollutant, for example pollen or tobacco smoke. So such kind of filter will be high efficiency particulate air filter. And as I told you, if we want to increase the efficiency of your electrostatic precipitator, then from 90 to 99, then we have to double the area. So for example, initial it was 3140 meter square area, then we have to increase the plate area double, so that we can increase the efficiency from 90 to 99%, because it was exponentially related to each other. So thank you so much. If you have any query or suggestion, you can let me know. Otherwise, we will meet next Monday 7 to 9, and you can contact me anytime if you have any kind of difficulty related to this kind of content. So thank you so much everyone to be very patient and listening it very patiently. Thank you so much, Venkatesh. Thank you so much everyone. So now you can leave and you can have your dinner. Good night.